We're going to be working with inverse circular functions, but before we can do that, we need to talk about how we're going to restrict the domains of some functions to make this work. So I'll work with this explaining with the inverse sine function, and then I'll give you the information for the inverse cosine, inverse cotangent, tangent, etc. But let's go ahead and start with what an inverse trig function is. An inverse trig function is something like y equals inverse sine of x, or y equals arc sine of x. These both mean the same thing. This means what angle in the interval negative pi over 2 to positive pi over 2, notice there's brackets here, has a sine of x. That's what this means. Now where does this interval come in? Well, let's go ahead and graph the sine graph real quick. Now the sine graph, if you'll recall, the sine of 0 is 0, so it starts down here, it goes as high as 1, and it goes as low as a negative 1. This is pi over 2 pi, 3 pi over 2, and 2 pi. So here's one full period of the sine function. And then I also want to move in this other direction, negative pi over 2, negative pi, etc. So first of all, when we're talking about inverse functions, the inverse functions have to pass a horizontal line test. Now if you recall, if something is a function, it passes the vertical line test. So if we took something like this, and if it never hit more than one point at the same time, passes the vertical line test, I know it's a function. But what an inverse function does is it has to pass a horizontal line test. So an example of a horizontal line test would be something like this. And if you notice right away, it doesn't pass that. It hits in 3 points, 1, 2, 3. So it fails the horizontal line test. And you might say, well, why are we learning about these if it fails the horizontal line test and an inverse can't exist? Well, what we do is we decide where to restrict it so it will pass the horizontal line test. So for this example, if we restrict this from negative pi over 2 to positive pi over 2, then it passes the horizontal line test through here. And you might say, well, why didn't you do 0 to pi? Well, it wouldn't pass the horizontal line test because of this piece over here. So we restrict it as close as we can to the origin, basically, and that's what we're going to be looking at. And we say, well, let's only consider the sine function from negative to positive pi over 2. So what we do is all mathematicians have agreed upon on how this will be restricted, because it could be restricted other places as well. And what we've done then is we can do this for each function: inverse cosine, inverse tangent, inverse cotangent, etc. And so let's go ahead and make a table of these restrictions, and you'll need to know these restrictions. So first of all, let's start with the inverse function. And also other quick note, you know, we write this as arc sine or inverse sine. These are interchangeable. You can use either one of these. However, please note, inverse sine of x does not equal 1 over sine of x. We're used to seeing like a exponent with a negative 1, and we think to flip it, but that's not what this notation means. This is a trigonometric notation that starts to talk about an inverse circular function. So we have inverse function, we have a domain for that inverse function. Then we have the range, and we're going to split the range up into two pieces: the range interval and the range quadrants. Okay, so let's go ahead and start with y equals inverse sine of x. And I'm going to call this arc sine, but remember, you could write it as inverse sine as well. So if we think about the picture that we just drew up here, this graph, the domain would be our x values. But this is not the inverse sine, this is just the sine. What happens are the domain and the range swap. So the range of this graph goes from negative 1 to positive 1, and that becomes the domain of the inverse. So the domain here is negative 1 to 1. Now we're going to develop the same idea without going through all the details for all of these functions. And again, there's other ways to restrict these functions. But what's happened is mathematicians have agreed to always restrict on the same values, so we always have that common frame of reference. And in your My Math Lab homework, you'll see the notation that I'm having here, the arcsecant, arccosecant, etc. You'll also see the inverse, the exponent with the -1 as well. They're interchangeable. Okay, so for the sine, the range interval then would be the domain of the regular, so that goes from negative to positive pi over 2. And again, you'll need to know these restrictions. Now the quadrants from negative to positive pi over 2 are quadrants 1 and quadrant 4. Now for arc cosine, my domain is still -1 to 1, because remember, the domain of the inverse is the range of the original. However, I have to restrict this one from 0 to pi. Because negative to positive pi over 2, what ends up happening is it doesn't pass the horizontal line test. So the quadrants here are 1 and 2. And we're going to work a lot of these problems so it'll be a little bit more clear. Domain negative to positive infinity. The range would be negative pi over 2 to positive pi over 2. Something I want you to note here is there's no brackets on the parentheses here. There are brackets for inverse sine but not for inverse tangent, and the reason is tangent is sine over cosine, and cosine is 0 at positive and negative pi over 2, so that would make the fraction undefined. So this would be quadrants 1 and 4 as well, but not the quadrantial angles. Arc cotangent has the same domain as arc tangent. The arc cotangent follows with cosine, so this would go 0 to pi, and this would be quadrants 1 and 2. And again, all of these are asking you a question: what angle, what angle, what angle, what angle. So I'm asking the question what angle, and that has to be the range, the output, has a particular sign of, that's the domain value. Okay, arcsecant. Now remember, these are built off of the other trig functions. So the domain here would be -infinity to -1, bracketed. Let me make sure that looks like a good bracket. Union 1 to infinity. Now the output here would be 0 to pi over 2. Notice there is a bracket there, parenthesis here. So that's quadrant 1. And then pi over 2 to pi. Now the pi has a bracket, and that would be quadrant 2. Now arc cosecant, -infinity to -1. Union 1 to infinity. And this is going to follow closer to the arc sine. So this would be negative pi over 2, it's bracketed as well, to 0, union 0 to pi over 2. Okay, and this would be quadrants 1 and 4. Now a lot of this isn't going to make sense until we see lots of problems, but I kind of wanted to get this table out there and these facts kind of out there so we could be working with those. Now one other thing that we'll want to know is how do we evaluate an inverse secant, inverse cosecant, inverse cotangent, since they're reciprocals. So the way that we want to remember that is the inverse secant is evaluated as the inverse cosine of 1 over whatever the argument is of the secant. The inverse cosecant is evaluated as inverse sine of 1 over x, and the inverse cotangent is evaluated, as you might guess, the inverse tangent of 1 over x. But this is only if x is greater than 0, and it's evaluated as the inverse tangent of 1 over x plus 180 degrees if x is greater than 0. Now if we were working with radians here, this would be pi, so plus pi if we're working with radians. So these are the kind of the big important things that we'll want to remember for this section. And what I want you to get used to is, first of all, being able to ask the question that's being asked of you when you look at one of these problems, and then also knowing what it's looking for. We're always looking for an angle. So we're just going to work a lot of these problems, and hopefully that'll help you out when you work through your My Math Lab homework and your handwritten homework. So for this first question I pulled in, this says find the exact value of the real number y if it exists. It says do not use a calculator. I would say do not use a calculator to check or to do the work, but use to check. Now a lot of these we won't be able to use our calculator on, but some we will be able to, so I'll show you how to use those as well. So first of all, what does this mean? Y equals inverse sine of -1/2. This means what angle in the interval from -π/2 to π/2 has a sine of -1/2. Okay, so if we come back up here, that negative to positive π/2, that came from right here. And again, that's why you have to have those memorized. You have to be able to say that because there's actually an infinite number of solutions unless we restrict that accordingly. And then again, if you don't restrict it, then an inverse doesn't exist at all. Now another way that we can write this or remember this is saying what angle in this interval has a sine of -1/2. Well, we could say, well, that's theta does. So then we could say, okay, well, the sine of theta is -1/2 then, where theta is in the interval negative to positive π/2. So that's another way that we could write this exact same thing. Well, if you know your unit circle, this won't be very hard. If you don't know your unit circle, these are going to be pretty tough. So first of all, it looks like to me on this one, the sine of π/6, or the sine of 60 degrees, is going to be 1/2, but this is a -1/2, so I need to rotate it into the fourth quadrant. So because this is negative, so sine of theta is negative, so this means quadrant 4. Now that doesn't mean that I can rotate through clear around to quadrant 4. What I need is this angle right here, because I need to be between -π/2 and a positive π/2. So I can't go outside of this region. So what I can say here then for theta then is that theta equals -π/6 or -30 degrees, depending on what the instructions are asking for. Now usually on My Math Lab, it'll give you some information. It'll say type an exact answer using pi as needed, and there's no degree symbol. That tells me we're working in radians then. So make sure that you kind of read through those instructions and answer accordingly. So what angle between negative and positive π/2 has a sine of -1/2? -π/6 or -30 degrees does. Well, how could we evaluate this on your calculator? Well, on your calculator, we have the inverse sine functions right above sine, cosine, and tangent. So let's go ahead and go to our home screen. And here's our inverse sine, so I'll go second inverse sine, and I put in a -1/2. Now you can use your fraction key if you want, or you could use a decimal of 0.5, it's up to you. And you can see we get this -0.523598. We are in radian mode, so let's see if our -π/6 is in a decimal equivalent to that. Yep, it's a decimal equivalent, so I know I'm right. Another thing that we could do is we could quickly change this to degree mode. And then we could do inverse sine of -1/2. And this time I'm going to do 0.5 here. And we could get the -30 degrees. So there's a couple different ways to do this. Now, on an exam, you could evaluate this and get -30, but there won't be any credit unless there's some work shown. And the work that I would be looking for is this type of work up here. This statement, what angle in this interval has a sine of -1/2? So this is the work I'm looking for, and this is the work that you'll be graded on. So make sure that you understand what's going on here. Your calculator won't always do all of these for you. It's a good way to check some of them, but again, it won't do all of them, so you have to be a little bit careful about that. Let's go ahead and pull in another. We'll do quite a few of these. Okay, this one is similar. It says find the exact value. This one we're working with inverse cosine. Now remember, from our table, inverse cosine is restricted to the first and second quadrants, so that's 0 to pi. So inverse cosine of negative square root of 3 over 2, this means what angle in the interval 0 to pi, and again that's from our table above, has a cosine of negative square root of 3 over 2. And I could say alpha does, or theta, or whatever your favorite angle value is. So what this means then is the cosine of alpha is equal to negative square root of 3 over 2, where alpha is in the interval 0 to pi. Okay, so that's what that means. So obviously cosine is negative, so we know we're in quadrant 2. So it has to be a multiple. Now this is a standard angle that I know about. Okay, so since I know about this, I should be able to look back to my unit circle or recreate that unit circle. And the cosine here would be some multiple of pi over 6. So in this particular case, alpha would equal 5 pi over 6, or 150 degrees depending on what the instructions are asking for. So I know it's going to be some multiple of pi over 6. It's going to be the angle in the second quadrant that has a reference angle of pi over 6. And again, I can check that on our calculator. Pull that in here. This would be the inverse cosine. I am in degree mode already. Let's get this to stay. So I'm going to go to inverse cosine. And this is going to be negative square root of 3 over 2. Okay, we're in degree mode, so there's my 150 degrees that we have here. And then of course I can convert that to radian if the instructions require it to 5 pi over 6. But again, you're not being graded on your answer, you're being graded on all this work. So you need to be able to write this statement: what angle in the interval 0 to pi has a cosine of, etc. And you need to be able to write this out, tell which quadrant that you're in and why you're in that quadrant, and then your other information here just comes from the fact that you know your reference angles and you know your unit circle. So that will work pretty slick. Okay, next. Let's go ahead and pull one up maybe that might be an inverse tangent here. Let's see if we can find one. Okay, this one is inverse tangent. They denote this arctan. So again, that notation is interchangeable. Because it says do not use a calculator, but you can also just think I can use a calculator to check, but I need to make sure that I'm showing all of my steps. So y equal arctan of 1. And just like I always said, always put parentheses around the arguments of your trig functions. Always put parentheses around the arguments of your inverse or your arc trig functions as well. So this means what angle in the interval from negative to positive pi over 2, no brackets here, has a tangent of 1. Okay, so another way that we could write this then is, I could say this one's beta does. Then we could say tangent of beta is equal to 1 then. And beta is in the interval negative to positive pi over 2, no brackets, just parentheses here. And you have to know those restrictions from the first table. You've got to know those, so it'd be a good idea to put them all on a note card or something. Okay, well, I know that the tangent of pi over 4 is 1, so this has to be a multiple of pi over 4. This is in the first quadrant, so tangent of beta is greater than 0, so beta is in quadrant 1. So therefore beta has to be pi over 4 or 45 degrees. But again, you need to read the instructions on the problem that you're given to see if they're looking for a multiple of pi, that would mean radians, or if they're looking for something in degrees. And usually if they have something in the degrees, there'll be a degree symbol involved, or it will specifically state that. So again, you've got to know the multiples here of your unit circle. You've got to know your unit circle, and if you don't know your unit circle and those restrictions, these will be pretty tough. Now let's go ahead and look at some inverse reciprocal functions like cosecant. These are a little bit different to evaluate. So it says find the exact value of the real number y if it exists. Do not use a calculator. But remember, you can use a calculator to check, but you won't have a correct answer unless you have the information that tells you about how you found it. So showing your work is ultimately important here. Okay, so let's go ahead and write out what this means. And again, this is the work that we'd want to show. Y equals inverse cosecant of -1. This means what angle in the interval. Now we have to remember our intervals here from our previous table up above, from -π/2 to 0, 0 to π/2. So basically that just means skipping 0. And there's a bracket at -π/2 and +π/2. Make sure you keep that in mind. Has a cosecant of -1. And remember, our calculators don't have a cosecant button, so when I evaluate this, I'm going to have to evaluate this a little bit differently. And it'll be easier for me to evaluate if I can write this in terms of sine and cosine, because I know those values for my unit circle. So let's go ahead and evaluate this as y equals inverse sine of 1 over the argument of -1. So this would be y equals inverse sine of -1. So this is asking the question, what angle? And I have to use the original interval. I can't switch it to the interval for inverse sine because I have to remember I'm really working with cosecant. So this would be -π/2, whoops, that's a 2, to 0. Has a sine of -1. And I could say something like theta or alpha or beta does. So this would mean the sine of theta is -1. And because I know my unit circle, that tells me that theta is -π/2 or -90 degrees. Okay, so again, you can work with those in degrees or radians. Just make sure when you work with the problem on my math lab that you answer what they're looking for in terms of degrees or radians. Let's go ahead and evaluate this on our calculator so we can check our answer. But remember, if you want credit for a problem like this, the work that I'm looking for is all of this. You can't just write an answer at the end. It's not going to be worth any points. You have to have the work to support it. Okay, so let's go ahead and look at inverse sine of -1. Now for this one, please also remember that it ended up being -1. Here's -90, and I'm in degree mode, so that worked perfect. Please remember that this isn't -1 right here and -1. These aren't the same. It's 1 over -1. So if this was a -2, this would be 1 over -2. So make sure that you don't just copy down that same value, but you realize it actually is a different value. Okay, let's go ahead and look at a few others as well. So for this one, we're working with inverse cotangent. Again, do not use a calculator. We're looking for an exact value. We'll be able to check this perhaps with our calculator, but you have to remember that I need to remember all the restrictions for our domains here. So let's go ahead and get started with this one. This is y equal inverse cotangent of -square root of 3 over 3. This means what angle in the interval. So now the interval that I want to use for inverse cotangent was 0 to pi. Let's keep that in mind, 0 to pi, has a cotangent of -square root of 3 over 3. Now if you knew that off the top of your head, you could just answer this right away. However, if you didn't, and we want to kind of convert these to tangent and inverse tangents, things that we know a little bit more about, what we could do then is we could rewrite this. So I want to evaluate this as y equals inverse tangent of 1 over -square root of 3 over 3. So this would be y equal inverse tangent of -3 over root 3, because this would flip. And of course, if we rationalize the denominator, y equal inverse tangent and negative 3 root 3 over 3. The 3's would cancel. And finally, y equals inverse tangent of negative root 3. So this means what angle in the interval, now I'm not using the interval for inverse tangent, I'm using the interval from up here, 0 to pi, has a tangent of negative root 3. Okay, so hopefully this is familiar to us from using the unit circle. This shouldn't be too hard to figure out, and if you know this, then we know we're negative, so we have to be in the quadrant 2 because we're between 0 and pi. So this is different. If this was just inverse tangent without the flip, because we started with inverse cotangent, this would be very different. So what I would look at here then is this has to be a multiple of pi over 3. It have to be in the second quadrant, so this would be 2 pi over 3. So let's say theta does. Okay, so then theta would equal 2 pi over 3. Now, this one is tricky because this changed the whole problem based on the fact that I started with inverse cotangent. Okay, so this changed. This is not the restriction that I would use for inverse tangent usually. It changed because it's the restriction that I use for inverse cotangent. So make sure you follow through with that because it's a really important idea. Now if we come up here to look at those original restrictions we were given at the very, very beginning, we had some things in here for inverse cotangent or arc cotangent that I needed to remember this flip. And when I evaluate, I had to keep in mind whether inverse tangent, when I flipped it, whether the argument was positive or negative. But we already took care of that. And actually this looks incorrect right here to me. I think this one should be less than 0. So I'm glad we came up and looked at that. So let me update that. That should be a less than 0. Whoops. Put it in red to make sure that we see that. Less than 0. So hopefully I said it right when I wrote and just wrote it wrong. But if I did both, that's a less than sign. So let's make sure we get that. Okay, so now let's see what happens with a calculator. If we were to do this problem on a calculator, this would be the inverse tangent, and I'm going to go ahead and put in the negative root 3 here. And we're in degree mode, so this is a negative 60 degrees. 2 pi over 3 is 120 degrees, so I guess I could include that. But the calculator says 60 degrees. Negative 60 degrees. So why is that? Well, this has to do with the fact that there's a different restriction for inverse tangent than there is for inverse cotangent. The way that we work this problem, it didn't matter because we got the right answer because we realized that there was that change. But if you work this problem without being aware of that restriction, then you'd get the incorrect answer. So that's why you can't rely on your calculators for these. So what I need to remember here then is I need to add that 180 degrees, which would give me that 120 degrees to match. And so that's why that plus 180 is up at the top in that table that we looked at. But if you work through the problem like I showed you up here, that won't end up being an issue. Okay, so we've looked at quite a few different types of problems. We've looked at inverse trig for secant, cosecant, cotangent, those types of problems. We've also looked at some problems where we're working with degrees and radians. We've kind of looked at both. But one thing I want you to keep in mind is sometimes there is no solution. So let's look at a problem where there's a potential of no solution. So let's look at inverse sine or arc sine. Whoops, everything disappeared here. Inverse sine or arc sine of negative 2. Okay, so now this means what angle in the interval from negative to positive pi over 2, points inclusive, meaning there's a bracket, has a sine of negative 2? And the answer is none. There's no solution to this because if you think about the sine graph, remember it started at the origin, it went up 1, down 1. There's no point at where this goes to negative 2 that we're looking at here. So there's no solution here. Now if you put this in your calculator, and again we've been working in degree mode, but remember these are interchangeable, we could do secant inverse sine and then put in a negative 2, and we should get some sort of an error message or not possible, something like that. Its error is domain, so that means that value of negative 2 that I'm plugging in is not possible. So again, that domain value, checking to see if it's even a possible answer is going to be important. And the best way to know that is if you know the graphs of your basic trig functions, which we learned in the last unit. Okay, let's go ahead and look at some more examples. Now these types of problems are some of the most fun to work, I think, because they're kind of like a puzzle inside of a puzzle. So we have to start on the inside of this problem and then kind of work toward the outside. So we're going to start on the inside where we're working with this arc cosine, and we're going to do the arc cosine part, and then when we're done with the arc cosine part, then we'll come out and do the tangent part. So oranges first. So let's start with y equals arc cosine of square root of 3 over 2. And again, this is how you show your work. If you want credit for these problems, this is how you show that work. You can't just plug them into your calculator and then make some conversions or something. Then you have to be able to show the logic in the process here. So this means what angle in the interval 0 to pi, points inclusive, meaning brackets, has a cosine of square root of 3 over 2. Well, this is a standard angle that we would know. It's in the first quadrant because cosine is positive, and the cosine of pi over 6 has a cosine of square root of 3 over 2. So what angle has a cosine of square root of 3 over 2? Pi over 6 does. And if you want to work in degrees, you can work in degrees as well. Now what we do is we put that into the next part. So the next part then would be, what is the tangent of that angle then? So what is the tangent of pi over 6? Now the tangent of pi over 6, this would probably be one that you might have memorized as square root of 3 over 3. But if you don't, remember that we can recreate that because we know tangent is sine of the angle over the cosine of the angle. The sine of pi over 6 is 1/2. The cosine of pi over 6 is square root of 3 over 2. And when you divide by a fraction, you actually multiply by the reciprocal. I'm left with 1 over root 3, rationalize the denominator, and I'm left with the square root of 3 over 3. So this whole thing right here equals the square root of 3 over 3. The inside part was saying what angle, and the outside part was asking for the value of that angle that you found. So these are kind of neat. Again, you always start on the inside and work toward the outside. And if you know your unit circle, these won't be too bad, but if you don't know your unit circle, they're going to be a lot more difficult. So if you don't quite have that memorized yet, make sure that you have a copy of that somewhere. Maybe you can draw one out and be able to reference it very quickly, so you'll be able to start learning the unit circle a little bit better. Okay, this one's interesting. I have no idea what angle has a tangent of -7. It's not a standard one that I'm aware of. So how would we work a problem like this? Again, same as last time, we're going to start on the inside, so we're going to start here, and then we'll work on the outside. So that would be the second step. So starting on the inside, this would be y equals inverse tangent of -7. This means what angle in the interval negative to positive pi over 2, not bracketed because they're undefined at those points. Okay. What angle in the interval negative to positive pi over 2 has a tangent of -7? And I don't know, so I'm just going to say theta does. Okay, so this means that the tangent of theta is -7. Well, if tangent is negative, that must mean I'm in quadrant 4. So let's go ahead and drop a quick quadrant 4 here, pop in our right triangle. You can use not only right triangle trig here, but you can use unit circle trig as well. And remember, tangent of theta equals -7 over 1 is equal to opposite over adjacent. So opposite of theta would be -7, adjacent would be 1. Now if you go through and use Pythagorean's theorem, then this would be the square root of 50, which is 25 times 2. Square root of 25 is 5, so this is 5 root 2. Now if you didn't follow, that would be a -7 quantity squared plus 1 squared equals that hypotenuse squared. So that's c squared equals 50. C equals plus or minus square root of 50, but we're looking at the hypotenuse here, so that would be the positive square root of 50. Root 25 root 2, 5 root 2. Okay, so now theta is this angle, and this next step says, okay, we'll find the cosine of that value of theta. Well, cosine is adjacent over hypotenuse, so the adjacent leg to theta is 1, the hypotenuse is 5 root 2, and then of course I rationalize that denominator and end up with root 2 over 5 times 2, which is the square root of 2 over 10. So this equals the square root of 2 over 10. So these are I really enjoy these. These are fun problems to be able to work with. Again, you always start on the inside and work toward the outside. And the work that we're looking for is all of this information right here. You can't just pop it into your calculator and get the decimal approximation for this. If you wanted to do that, you could use it to check it, but in terms of points for credit, there are no points here unless you have all the work. Okay, let's see if we can find some more problems that are a little bit more interesting like that one. So again, those come across when we have a problem where we don't know the standard angle. This is an interesting one. There's a lot going on with this one. We're going to be applying some things that we learned in the last unit to this. So this is cosine of inverse tangent minus another inverse tangent. Well, let's remember what these mean. This is some angle and this is some other angle. So what I'm going to do is I'm going to call this one, we'll say alpha, and this one beta, because I know they're some angle, because remember inverse trig function, I say what angle, what angle, what angle. So this looks like cosine of alpha minus beta. Now this should be a little bit familiar to you from the last unit. The cosine of alpha minus beta is the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. So that's what I need to do. I need to figure out what is the cosine and sine of alpha and what is the cosine and sine of beta. And then I can plug that in to each of these values and figure out what's going on here. Another thing, tangent is negative for the first one, so if tangent is negative for the first one, that tells me for alpha that the sine will be negative as well. Cosine will be positive because I'm in quadrant 4. So let's see how this is going to work. I'm going to leave a little space up here at the top so I can work through this solution when I get to it. So let's go ahead and look at alpha equals the inverse tangent of -5 over 12. And it's called alpha because I named it alpha. So what angle has a tangent of -5 over 12? What angle in the interval from negative to positive pi over 2 has a tangent of -5 over 12? And I don't know, so I'm just going to call it alpha. That's where the alpha came from. So this means that the tangent of alpha equals -5 over 12. So what I can do here is draw a triangle in the fourth quadrant then, and from that triangle in the fourth quadrant I can use the Pythagorean theorem to come up with the sine and cosine eventually. So here's my fourth quadrant. Draw that triangle. My right angle, here's alpha. So again, this is opposite and adjacent, so SOHCAHTOA. So opposite, the negative has to go with the opposite because I'm in the fourth quadrant, and here's my adjacent. Now if I want to solve for this missing side, then that would be 12 squared plus a negative 5 quantity squared equals c squared. 144 plus 25, that's 169. So c would equal square root of 169, which is 13. Okay, so that one I should be able to find the cosine and sine of now. So let's go ahead and pop that back up here. The cosine of alpha would be adjacent over hypotenuse, so that would be 12 over 13. And the sine of alpha would be the opposite from alpha, which would be a negative 5 over 13. Now let's go ahead and do the same for b. In this case, beta is equal to the inverse tangent. Let's see what that was. I think it was 4/3. So again, this means what angle in the interval negative to positive pi over 2, no brackets, has a tangent of 4/3? And the answer is beta. So the tangent of beta is equal to 4/3. Well, that's opposite over adjacent. Tangent is positive here, so this must mean I'm in quadrant 1. So let's go ahead and pop this up into quadrant 1. Let's label beta in my right angle. Tangent is opposite over adjacent. If I want to find this missing side, that would be 4 squared plus 3 squared equals c squared. 16 plus 9. C is equal to 5. And then what I can do from here is I can plug that in up here. So cosine of beta would be adjacent over hypotenuse. And the sine of beta would be opposite over hypotenuse. Okay, and then simplifying from here, 12 times 3 is 36. 13 times 5 is 85. Minus 5 times 4 is 20 over 85. 36 minus 20 is 16/85. So that would be the cosine of alpha minus beta. And of course that went clear back to, I'm sorry, that's not 85, it's 65. The practice problem I was looking at had a 17 there. So it says 65. So this is equal to 16 over 65. Okay? So that's the cosine of the inverse tangent of minus the inverse tangent of. So again, it's important to keep these in mind in terms of breaking them up into another trig identity that we used from the last section. So these problems can get kind of long, but they are very, very interesting. Now this next one that we're going to be looking at, we're not using numbers per se, we're using an algebraic expression, in this case u over 5. Okay, so let's go ahead and think about how to start this one. This is 2 inverse secant of u over 5. So this is 2 times an angle that has a secant of u over 5. So a good way to start this would be to think about how we could evaluate inverse secant. So remember, when we start talking about working on the inside, let's focus on this right here. I'm going to go ahead and call this, I guess we could call it alpha or something like that. So I'm going to call this alpha. So what this actually looks like is the sine of 2 alpha. And there's a nice trig identity that says the sine of 2 alpha is equal to 2 sine of alpha cosine of alpha. So we need to be able to work with this alpha. Now from here, what I would do is I would think about what this means. This means what angle in the interval. Okay, so this is that tricky one. 0 to pi over 2, pi over 2 to pi. Basically that means that we can't touch pi over 2 here. Has a secant of u over 5. And we have no idea, so we say alpha does. So then what we can do is we can evaluate this as an inverse cosine. Okay, so from here what I would do is I would have alpha equals inverse cosine, and this would be flipped, of 5 over u. Because remember, the thing we need to remember here is u over 5 flips. Now I need to keep the same restriction. As the inverse secant. And that was from right here. Okay, well I don't know the answer to this either, so what we need to do is we need to put up a triangle. Now inverse secant, this argument is positive, so that means I'm in quadrant 1, because I have quadrant 1 basically is here. Quadrant 2 is here, so I know I'm in quadrant 1. So let's go ahead and pop up that triangle. So this is my alpha. Cosine is adjacent over hypotenuse, which makes this missing side, I'll put it in a different color, this missing side that's opposite from alpha would be equal to the square root of u squared minus 25 using Pythagorean's theorem, and you can verify that. Okay, now for my formula up here, remember the sine of 2 theta, or 2 alpha we'll say, was 2 sine alpha cosine of alpha. Well, the sine of alpha I can figure out from up here. Sine is opposite, so this would be opposite over hypotenuse. And we already know cosine was 5 over u because that was given to me right here. Or I could look at it and say adjacent over hypotenuse. And so here I have 2 times 5 is 10 square roots of u squared minus 25 all over u squared. And that's what my solution would be here. So again, I should be able to work with these in terms of numbers and algebraic expressions. Remembering your SOHCAHTOA, you could also use your unit circles, trig, sine squared plus cosine squared is 1 to work with these as well. As usual, if you have any questions, let me know. I'm happy to help, and good luck.